Everybody, so this is basically, remember I told you that since we didn't get to it in class, I was going to do a quick proof of page 68. So please make sure you're kind of filling this in with me as I go through. So they give you a parallelogram. Now, whenever they give you a parallelogram as a picture, if you're doing a proof, you really want to fill in not only the vertices. So we're going to call this A, B. So if you go around the parallelogram, you could call this AB and you could call this C. You cannot call this C. So when you go around, you can't like jump. So you could go A, B, C, D, or you could have gone this way, A, B, C, D. You could have really put A anywhere. But once you put the A and the B, now we're just going to go around the parallelogram. And it says if a quadrilateral is a parallelogram, then opposite sides are congruent. So we don't know that opposite sides are congruent. Now, here's the deal. You do know opposite sides are congruent in any parallelogram. We learned that that is a property. So what you're doing now is you're proving that one of the properties always works. Now, when you have to do a quadrilateral property proof, when you can, you only really want to use the definition of that quadrilateral. And if you can't prove it just using the definition, you can use other properties. But what you can't do is say automatically the opposite sides are congruent, because that's what we're trying to prove. So what I'm going to do is I'm going to assume whenever you do these quadrilateral proofs, I'm going to go ahead and draw one of the diagonals. Maybe we'll need both, but I'm just going to draw one of them. Okay. So how am I going to get opposite sides to be congruent? Well, if I get these two triangles to be congruent, then these two sides have to be congruent because of CPCTC. Same thing with these two sides. So that's what I'm going to try to do. Let's see if I can do it. So first of all, we know, and then please remember, I'm typing this, so it's kind of hard sometimes to type these. So I'm not going to use the proper notation, but I will tell you when I'm not using the proper notation so that you can, when you're doing this, make sure you do the proper notation. All right, so first of all, here are my statements. Write statements, where I can just write an S, and here are my reasons. So statement number one, we got to start with the given. It's telling us if the quadrilateral is parallelogram, so that means the given is ABCD is a parallelogram. Okay, and the reason why that is going to be obviously given. Now, based on the fact that it's a parallelogram, actually, even before that, I noticed that these two triangles share side DB. But remember, side DB is actually going to be equal to BD. And that's because this angle B is actually going to be this angle equal to the other angle D in a parallelogram. So that is the symmetric property. And, and then I also know that line AB is parallel to line DC, and also the other opposite are true. AD is going to be parallel to BC. I'm going to go ahead and write the parallel marks. So, excuse me, let me get those in. All right. And the reason why those two sides are parallel to each other is because, remember, we already said it was a given that it's a parallelogram. That is the definition of a parallelogram. Okay. Not writing out the whole word, but you should. And also, I didn't put this correctly. When you're talking about two sides being parallel, we can't talk about the measures of them. We have to call them line AB and line DC, and line AD and line BC. Okay? So now we know that those are parallel. Now, why is that going to help us? Let's see. Okay, when you have parallel lines, I know, for example, that angle 1 and angle 2 are going to be congruent. Those are alternate interior angles. So I'm going to write that. Again, you should say the measure of angle 1. Actually, we could use congruent. So we can say angle 1, sorry about that, Mark, is congruent, sorry guys, is congruent to angle 2, because those are alternate interior angles theorem. Obviously didn't write that all out. And then also we can say that based on these being parallel, we could also say that 3 and 4 are congruent. And that's also because of the alternate interior angle theorem. Sorry about my handwriting, I'm writing on the screen. So Now, let's see what we got. We got this is congruent to this, and this is congruent to this, and we got that side equal. Well, if you look at those two triangles are definitely equal. Why are they equal? Well, why are they congruent? Because of angle, side angle. So now we know that triangle ABD is congruent. This would go down here, obviously. Is congruent to triangle, and then we got to be really careful because angle A is congruent to angle C. Angle B is congruent to angle D. And angle D is congruent to angle B. So I'd call it CDB and triangle ABD. Now the reason why, remember, is that's the angle side angle postulate. That would go down there. Then once I say that those are equal, I can say that line AD is congruent, or in this case, I said AB. AB and DC are congruent. Why? That's CP, CTC. And then I can also say that, and I'm sorry for the handwriting, but I'm basically saying these two are congruent because of CPCTC, and I'm also going to be saying in my proof these two are congruent because of CPCTC. And my last line is, I've basically proven if a quadrilateral parallelogram, opposite sides are congruent. Because I've proven, you can stop right there. You don't have to actually say that line because you've already proven AD and BC. So knowing that it was a parallelogram, I've just proven that every parallelogram is going to have that property, that opposite sides are going to be equal. Not necessarily all equal, but they're definitely opposite sides are equal. So maybe this one's 7 and this one's 7 and this one's 8, this one's 8, whatever it is. Okay? All right, so I hope that helps.